We will look at the central limit theorem in case of continuous random variable and what it means exactly, and then we will also formalize it. Let's say we have a uniform distribution, and in this distribution, the random variable represents the amount of time that is taken to answer a call in a customer service. Now let's say we started with the uniform distribution, and let's say the maximum is 10 minutes and the minimum is 1 minute. 1, 10. And then our uniform distribution will look like this. Because it's basically a probability distribution, and this is the random variable x. And for each minute, the probability is the same. Let's say it's y here. And what we can do here, we can sample this distribution each time with n number of samples, and we can increase the sample as the time goes by. So first, what we can do, we can make the sample size 1. So what it means that we take a number, a random time from the distribution, then we look at its probability. And let's denote our sample as y1, which is x1 divided by 1. And if it's y2, then we take 2 random waiting times and we divide it by 2, and y3 the same way, and we divide it by 4. And as you know, we started with a uniform distribution, and what we do, we record the average of all n experiments. And in the first case, if we draw the distribution of first random variable y1, we'll get approximately something like this. Okay, it seems that it doesn't work. Okay, we get something like this. Say we took 1, 2, 3, 4, 5, and etc. And 1 minute, 2 minutes. Say this is 2.5 here. So this is actually a density histogram. So what is density histogram? It's like some way of estimating its PDF. So what we did, we took samples, and each time when it was 3, we piled up. For example, first it was like this, histogram was like this, and we took a random sample, and the average time was 3, and then we added 1 here. And next time it was again when we come across 3 in our random sample, we add 1 more, and the same way here. Say and to turn it into a density histogram, we for example, how many points were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total number of 16. And for example, for this one, which is 4, 1, 2, 3, 4. And let's say this is 3. 4 divided by 16, and we also multiply it by the bin width. For example, if the bin width is 1, then it will be just 4 over 16. So the density estimation of this point will be 4 over 16. But let's say if it was 2, bin width was 2, then what will happen is that for, let's say this is 4. And this is 4.4 over 16. Let's say if it's now let's say this is 16. Yeah. And let's say we, for example, before it was like this, 3 and 4. And if our bin width is 2, then what we do exactly here is that we take 3 and 4, both of them, and in the density histogram, we want to calculate their density estimate. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. So it will be for 3 and 4, it will be just something like this. 4. Yeah, you can say like 3. Then at this point, 5 starts. Yeah, we denote it as 3, let's say. And this is 2. And let's calculate the density of this point. Then what we do exactly is that we 12 multiplied, divided by how many points we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's make it 13. And how many points do we have? 3, 3, 6, 19. 1, 2, 3, 4, 5, 6, 25 total points multiplied by 2. So the density of this will be 13 divided by 50. So what it actually means? It means that the probability of observing a point between 3 and 4, that's what exactly will give us. So coming back to here, what we did here, we started with y1, and each time we took a sample and we had its density histogram, and you can see that our density histogram distribution still looks similar to the uniform distribution. Why? Because we just used one point here. And in case of if we take y2 and draw its density histogram, actually the distribution will have a more bell-shaped. Would be something like this. Okay, let's do this like that. 0, 2, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. So what we did here exactly, each time we took a sample out of our population, the sample was the mean of so what did we did exactly? Each time we took two random sample out of the population, and then we took the average of these. And each time, for example, that number, the average of two random variables, for example, was 6 here, we added 1 here. And the next time was that we added one more. We added one more. Every time we bumped into 6, which was the average of two randomly drawn samples out of the population, we added it up, and we did it for all of the points, and it's more like bell shaped. And it turns out that as we go on, we do it with y3. Each time we take 3 random variables, and then we calculate their mean. We calculate their mean and plot those means, plot the distribution of those means. That plot will be more like bell-shaped. So as n increases, our distribution of yn gets closer to normal distribution. So that was basically central limit theorem in case of continuous variables. And we started with uniform distribution, and as we increased n, we ended up with a normal distribution. And here we will go with some formulas here. So as you can remember, we have had yn, and yn was basically we calculated xi's and from 1 to n, and then we divided it by their number. And let's calculate the expected value of this distribution, expected value of this random variable. So then what we do here, we take the expected value of this n xi, then we can actually write it as 1 over n, because 1 over n is inside the expected value. It's a constant, so we can take it out, and then we end up with expected value of this expression of this thing here, n1, and then it is equal to 1 over n, and we add this xi up n times, so it means like we multiplied it by n, and it also comes out n, and the expected value of x, yes, expected value of x. So these n's cancel out, and we end up with x. So what it means that no matter what, if it was uniform distribution or whatever it was, and we take the averages and plot the averages of samples, and we increase the n's, and each time we plot their distributions, the mean of that distribution doesn't change. The mean of distribution is the same as the random variable itself. So this random variable, let's say it was 7.5. So our conclusion was that as we increase the n and plot the distribution of averages, and when we increase n, it is expected value mean does not change. But what about the variance? Let's see if it's also true for the variance, and let's take the variance of yn, and then it's the variance of 1n xi and 1. And as you know, the constant comes out of the variation as squared, so we have 1n squared. And we also have this property, which is variance of x plus y is the variance of x plus variance of y in case the x and y are independent random variables. And we also will apply the same thing here, and it means that variance xi yes, and what happens here is that a variance xi is n, and it means that we multiply variance xi n times, so n comes out n multiplied by variance x, not xi, actually x, I'm sorry. I also write x here, which is x, and it is variance x divided by n. And now we see how the variance of yn changes as we increase n. The variance of yn decreases as we increase n, as you can see from this formula. And in our original uniform distribution, the variance x was 18.75. And our u random variable, and if we want to normalize it, then we have yn minus expected value of x and divided by so what was the variance of yn? Because when we standardize distribution, first we decrease the expected value from each point, and then we divide each point by the standard deviation, and standard deviation is basically this variance. And what was our variance? Our variance was variance x n, and we take the square root, and then we can write it as variance x, and this comes at the top. So mathematically, as n, so this is basically the standard deviation. Standard deviation of x. And mathematically, what it means that as n goes to infinity, this becomes a distribution of normal distribution of 0 and 1 squared. So it means like this equation here will will be a normal distribution with mean of 0 and standard deviation of 1, because we are normalizing it. Okay, that's it.